reactions? In this lecture, we're going to discuss two common classification schemes used to describe chemical reactions. Chemists use either scheme intuitively, depending on their needs, and there is a myriad of reaction examples that demonstrate the futility in placing them in just one's classification. But we have to try. So we'll use simple reactions to highlight the differences in reaction types as we go along. So let's get started. The first method that we will describe involves a pattern recognition approach and focuses on how the atoms move between compounds as we go from reactants to products in the bond-breaking making process of the reaction. We will look at four categories or reaction types in this classification scheme. First, let us assume a kind of labeling as we talk about these different processes. The letters A, B, C, and D symbolize atoms or groups of atoms such as polyatomic ions, and we'll observe how they move about in our generic model chemical equations. We will also look at specific examples of each reaction type. The first type of reaction is called a synthesis or combination reaction, and the equation looks like A plus B yields AB. An example reaction is magnesium metal combining with oxygen to make the solid compound magnesium oxide. The balanced reaction is magnesium solid plus 1/2 oxygen gas yields magnesium oxide solid. Now we can see that it looks like our generic form where a magnesium atom and oxygen atom combine to make a new compound. Of course, if we multiply this reaction by 2, we get the balanced equation that is shown. But now it's a bit harder to figure out what is going on. Now, the second type of reaction is called a decomposition reaction. The generic equation looks like this. AB yields A plus B. An example reaction involves calcium carbonate or limestone, which can decompose to make calcium oxide solid and carbon dioxide gas. The balanced reaction is shown. Now, the third type of reaction is called a single displacement reaction. The generic equation is A plus BC yields AC plus B. An example of this type of reaction is demonstrated by another type of hydrogen production reaction where sodium solid is thrown into water and produces the base, sodium hydroxide in water, and hydrogen gas. Balancing atoms leads to sodium solid plus H2O liquid yields sodium hydroxide aqueous plus 1/2 hydrogen gas, which looks like our generic equation where the sodium atom is displacing one of the hydrogen atoms in the water. Again, multiplying the equation by 2 yields the equation that is shown without the fractions. The fourth and last type of reaction we'll discuss using this classification scheme is the double displacement reaction. The generic equation here is AB plus CD yields AD plus CB. One of the classic examples of this reaction is an acid-base neutralization where aqueous hydrochloric acid and the base, sodium hydroxide, make water and the aqueous electrolyte, sodium chloride. The balanced reaction is shown. The HCl and sodium hydroxide chemicals trade partners to produce water in the aqueous sodium chloride salt solutions. The second way to categorize reactions is by looking at the type of chemistry or phenomenon that occurs during the reaction, such as the production of a precipitate or the transfer of electrons. This categorization is by far the most useful of the two classification schemes. The three general reaction types are precipitation reactions, acid-base reactions, and reduction-oxidation reactions, or in short, redox reactions. Each of these types of reactions will be fleshed out with individual lectures in subsequent videos. For now, we'll just content ourselves with some general definitions so you see all the reaction types in one place. The The first reaction type is precipitation reactions, where we typically mix two solutions containing dissolved ionic compounds usually, and when they combine they form solids called precipitates that fall out of the liquid. If the precipitate doesn't form, no reaction occurs. An example of this reaction is lead nitrate aqueous plus 2 potassium iodides yields lead iodide plus 2 potassium nitrate aqueous solutions. To understand and predict the outcome of these reactions in water, it is extremely useful to have the solubility rules at hand. The next type of reaction is acid-base reactions. They are, just as they sound, reactions between acids and bases. The key to identifying these reactions is our ability to identify acids and bases in the first place, so memorization of the common acids and bases is invaluable. The common acid-base reaction is the neutralization reaction in water. The acid and base react to form water and an electrolyte or salt. An example of this reaction came up earlier where hydrochloric acid and the base, sodium hydroxide, react and neutralize each other to yield water and the salt, sodium chloride. The last chemical process we'll cover in this lecture series is the oxidation-reduction reactions, or what we call redox reactions. This reaction type occurs when electrons move between atoms in a chemical process. To quickly identify these reactions, we must have a solid grasp of the common charges that atoms tend to want to achieve to be octets, and have a very solid grasp on the charges and identification of polyatomic ions. When we see any of these charges changing, we know we have an oxidation-reduction reaction. Again, we'll use as an earlier example the magnesium-oxygen reaction. In the elemental form, both the magnesium and oxygen elements on the reactant side are charge neutral, but on the product side we have a compound, magnesium oxide. In a molecule, we know that oxygen desires 2 electrons to be an octet, so it has what we call a charge or oxidation state of -2. There was only one source of electrons available to it, the alkali earth magnesium metal, which we know would love to have a +2 charge to be noble. In effect, electrons are transferred in the reaction, and this is the hallmark and identifier of a redox reaction. Again, we're going to expand on each of these reaction types in subsequent lectures, so get ready for a lot more chemistry. See you there!